This video tutorial will show how to model, analyze, and design a 3-span flanged post-tension beam in ADAPT PT-RC 2019. This is an accompanying video to a one-way slab example located on the same playlist page. We recommend you watch that video prior to this beam video, as that video will define many of the inputs in the program that are shared between one-way slabs, two-way slabs, and beams for design in the software. In this video, we're going to summarize the one-way slab model, and we're also going to define only those input parameters that affect post-tension beam design in the program. So to start, we're going to go ahead and launch ADAPT PT-RC 2019, and we're going to open the one-way slab model. In the PT input, we're going to use the option to edit data. We'll go up here to geometry. We can see we have a 7-span system, and we have these transverse beams modeled as the supports for the one-way slab. So these are actually the beams now that we're going to set up in the beam example. We'll go over here to geometry, and if we go to support geometry, we can see, let's go back one. We can see that the height of the beam is 21 inches, the width of the beam is 12 and 12, so that's 24 inches. We're going to be designing 24 by 21 inch beams. Now, one method of doing this, and we'll just take one of these interior beams as an example. One method is actually to use the reactions that you solve in the one-way slab and actually apply those reactions as a line load on the effective or on the T-beam. Another option would just be to use the tributary. So we're going to model a T-beam which is 27.5 feet as the flange. This is the full flange, and we'll model the 21 by 24 beam with that flange. The program will calculate the B effective and use those properties for the design of the beam and for the calculation of stresses, etc. So just wanted to point out that if you use the reactions that are solved for in the one-way slab example, those could actually be used as line loads because this beam is actually, 3-span. We might have a column. So we're going to set up a system that looks like this. In this case, the beam spans are going to be 34 feet. We're going to do a 34 foot, a 28 foot, and a 34 foot span. So we have a 3-span condition. We're going to assume that the columns are 24-inch square columns, 10 feet high. That's the height of the column, and we're going to check the beam design with columns below the structure versus below and above. So there's options for both. We're going to assume only supports below. Okay, so that's our summary for this tutorial. Let's go ahead now. I'm going to go back over to File. I'm going to select New, and we're going to set this up as a beam design. Because the geometry at every design cut, if we take, for example, this little image here, and we cut the beam at 20 sections, all of those are identical on each span. So we're going to use conventional geometry. The two-way slab example that's part of this series will show how to input segmented geometry. So we're going to be using conventional. It just means that the geometry per span is prismatic. We will use effective width in bending. This just means that the program will calculate the effective width for us based on the design code that we select. So let's go ahead and we'll use the same design code here, ACI 31814, for the design of the beam. These were defined in the one-way slab example. The only option here that might look slightly different might be the ability to increase moment of inertia over support. Equivalent frame method is inactive. That applies only to the two-way slab selection. So let's go ahead, say next. We're going to leave those design and user settings alone. We're now going to input the geometry of the beam. So we'll go to a 3-span condition. These are T-beams. They're prismatic. Notice if you try to change the prismatic to non-prismatic, that's actually locked out because we're using conventional input. And then we could change this to any of these sections. These two sections are inactive only because we're using effective flange. When you turn off effective flange, then you have the ability to model the I/L or the extended T section. So I'll show that. If I come back here to the general settings, I'll select no. And if I come back into the geometry, now I have the ability to select those two section types. Let's go back to general settings. Notice you can select the pull down menu options to go to any of the input fields, or we can use the next and back buttons in the wizard to go to those fields. We'll come back over here to our system. We'll do a 34, 28, 34-foot span. The width of the flange is going to be 27.5 feet. That's 330 inches. Okay, the height of the beam is 21. The width of the, this should be, the B should be 24, and this should be 330. Okay, the height of the flange, I believe, is 7 inches from the one-way slab example. So we have something set up like this. The structural view will come into focus. If you hover over any of the different spans, you can see that at the bottom left of the structure view window, you see some of the characteristics of the geometry of that span. So for the reference height, we're going to set this equal to 21. I'll set that equal to the height of the beam only because I want the control points for the tendons to be referenced from the soffit upward as positive values. If I go to a top view, we can see that the 330 inches, half of this, the multiplier left and right, half of it goes to the left side, this is left, half of it goes to the right side. So this is going to be 165 inches to the left, 165 inches to the right. This allows you to, if I had an opening here, I could input the geometry here and then shift it vertically using these multipliers. So, and that will be shown also in the two-way slab example if you check out that video in the same playlist. All right, we'll go to next. This will show the effective flange calculation. So if I stretch this out and I'm using ACI 313, these are the effective flanges that width that is calculated by the program. You can do user input and override these values if needed. This also uses European code if you wanted to use that code for some reason when you're selecting a different international code in the software. We're going to use lower columns. The column height we said will be 10 feet. Below it's going to be a 24 by 24. Okay, B is the dimension in this direction. D is the dimension along the span. That's the dimension of the column. DC represents a circular, just the diameter of the column, and then this percentage will allow you to modify the stiffness of the column. 100% is full stiffness. Less than that would obviously be a reduction in the column bending and axial stiffness in the solution. Okay, the left edge and right edge, those apply only to two-way slabs. This dictates how the program handles the punching shear check. We're going to assume here, let me go back to this view. We'll assume that we have lower column. This is lower column near, lower column far. This is the near side. This is the far side. This just dictates the condition, the boundary condition, so it's fixed, pinned, or roller. In this case, we have fixity at both top and bottom. And then the program will use cutoff lengths at face of column to calculate reinforcement and strength demand and also stress when we have a post-tension system. So we use a support width is 24. That's the dimension in the D direction. This is D. If you wanted to override the 24 inches, you could deselect this and then input the values here in those cells. For loading, we define kind of how the loading menu is set up in the one-way slab video, but briefly you can use any of these descriptions. The second character here, U, P, C, M, you can drag and drop, or you can just type in that load type classification using the second character, and that will fill out the parameters used to define the load. Span, if we select, for example, all here, that will fill out all spans. So we're going to just do some simple loading here. In this case, we'll do superimpose dead and live. We're going to have the program automatically calculate self-weight, and we can also turn on skip live load for the system if needed. So we'll do uniform load. The live load or the superimposed dead load we're going to say is 20 PSF. The live load say is 50 PSF. And again, any of these different types of loads can be applied to the structure. It's pretty straightforward in terms of how the loads are applied, what geometric characteristics are entered to define the position of the load and the magnitude of the loads. If you choose not to have the program calculate self-weight, we can select no, and then we now have a new classification here for self-weight. So if you're using something different than normal weight concrete, notice this, if I deselect this, I can then modify the unit weight. Otherwise, the program uses what's specified here. If I go to semi-lightweight and come back, this gets updated per this selection. So be mindful of that. In the concrete strength at 28 days, we're going to change this to 5,000. If you press tab, the modulus does not update, so you'd have to manually update this. If you press enter, this gets updated, and enter would then sequence through the different cells. So we'll go down here to concrete strength at initial condition. We'll say that's 3,500 psi. That's typically around 70 to 75% of F prime C. This would be like 7-day strength, for example, whenever you stress the cables. Column strength, similar input, 5,000, and we'll make sure we press enter. We have our longitudinal and shear reinforcement specifications here, bar size and grade of steel and modulus. So let's go ahead and set those up. I'll use number 4 stirrups with 2 legs, and then we'll use 60 KSI for the yield strength of the bar material. For the post-tensioning, we're going to use unbonded PT in this example. Okay, if we use bonded PT, that just changes the way the program treats, for example, minimum reinforcement and also loss calculations if you use the calculated option. So unbonded, we'll use a 1/2-inch diameter cable, 270 for FPU, and then the effective stress we're assuming is 175. If the user has control over what effective force you want. So by default, the program using 175 and 0.153, this would basically, if you multiply these two, this gives you an effective force of 26.7 kips. If you want something less or greater than this number, then you should adjust this value for your assumption for effective stress in the cable. This assumes short-term friction loss and seating loss and also long-term losses. So this is using really the effective force method versus the calculated force method in the software. If you want to enter base reinforcement, we show that example in the one-way slab video. This would allow the user to go in and enter specified base reinforcement or user-defined reinforcement at different positions in each span. We'll say that this is a new design. So we're going to select no there. We want the program to calculate all of the reinforcement. For the allowable stresses, the program is going to make checks against your tension and compression allowable stress. So either if it's greater than the input here, it'll be no good. If it's less, it will be good or okay. It's trying to target a force and profile that meets these conditions. This is one of the 3 different pieces of the criteria that we use to calculate the profile and the force of the cable in the beams. So for ACI, this number could be anywhere from 7.5 or even lower up to more than 12. The program is built for transition zone designs. It's not built for cracked zone where you have allowable stresses in tension greater than 12 F prime C, square root of F prime C. So if you do have a condition like that, I recommend you contact our support staff to discuss it with them. You can contact them at support@adaptsoft.com. So for this design, we're going to limit the stress for sustained and total condition to 7.5 square root of F prime C. This is kind of the bottom end of that transition zone between cracked and uncracked conditions. these compressive stresses come right in from the code that it's selected. For the pre-compression, we're targeting, let's say, 150 to 400 psi. And the percentage of dead load, we're going to balance, let's say, 50 to 100% of dead load to balance. The program will then use these as second and third pieces of the criteria to solve this puzzle or to design, let's say, the beams. So the design method can be either effective force, where let's assume that this is our live end, this is our dead end for our cable, and we might have, 3 reverse parabolas in here. If we were to graph the losses here, we might have a loss diagram that looks like this. If we actually calculate the losses, plus we have some seating loss. So if we take this diagram, this would be based on, let's say, the actual condition. So the actual condition here looks like this. We vary in force along the length of the cable, but when we're using effective force, we're saying, well, the average of that is something like, let me get my marker here, average of that is something like this. This is 26.7 kips per cable. So if you use force selection, we're always assuming this blue line. If you use calculated force method, then we use this pink line here. The program will calculate the force along the path of the cable. Okay, so let's use force method in this example. If you do select calculated, notice this then expands into different parameters for the calculation of the losses for the cables in the tendon. So, and then in the what we call the recycler window, you have the ability then to use either method when this option is selected. Okay, in this input window, we're going to define the tendon profile for each of our spans. And I'll go back to my elevation view. There's 3 different tendons defined here, and these are defined in more detail again in the one-way slab example. Tendon A is what we're going to use to design this 3-span system, and tendon A would be represented through all 3 spans. So tendon B and C can be represented in any span. So tendon B, for example, might be an add tendon where we represent it in this span, and then we anchor here, and this might be tendon C, B, and then A is the tendon through all 3 spans. In this table below, we define the different shapes of the tendons. So we're going to be using a reverse parabola for tendon A, B, and C with the inflection points x1, x2, x3 over L for defining that parabolic shape. If we do use tendons B and C, and the one-way slab example actually shows this in its design, you then can set up where the tail anchors behind the support here based on this input here, and whether or not it anchors at centroid or follows the shape of the parabola, and that's defined in these inputs here. So for this example, we're going to do something a little different than we did in the one-way slab example. We're going to just use tendon A only. That actually might mean that we over-design span 2, but since we have a majority of spans which are longer than span 2, the force necessary to meet the required design inputs or parameters are going to likely be dictated by span 1 and 3. The next input is the cover. For this beam design, we're going to use this is criteria cover and also CG for the post-tensioning. So the CG from top fiber, we're going to use 2.0 inches, and then from bottom we'll use 2.5. For the cover, for the reinforcement, I'll just use 1 top and bottom. The next option is defining how the program basically lays out the reinforcement needed that supplements the post-tensioning. This is the cutoff lengths for over support and in span for minimum reinforcement, and then also the extension of bars beyond point of 0 moment, or point of where the moment is, or the area of still is no longer needed for strength design. It's beyond, for example, this is 12 inches. So if I have a moment diagram that looks something like this, and let's say we're designing this span here for strength and we need reinforcement, the program would find the points of inflection or 0 moment It would also find basically where the moment gets cut in half about this curve, and we would need then long bars. So one long bar, if I project this down, this bar here would be, shouldn't call this long bar, this is, let's say, the bar that meets the maximum demand, and then we might need additional bars here where this area of still 1 plus area still 2 meets this moment. At the cutoff point, we extend this by this distance, 12 inches, and then the extension for this longer bar here meets this moment at this location here. So the program's algorithm does some cutoff of the bars, and you may see multiple bars in a span based on this. So this is just applicable to the extension of the different bars, short and long, that the program is calculating. If we go into the next input window, this is a curtailment schedule where the user can customize how the bars are actually laid out in each of the spans, top and bottom bars. So this is more of a just a default kind of simplified form of how the bars get laid out. This is the legacy way that the program has done this, and this gives the user more control over the extension beyond supports, beyond point of midspan moments, etc. And this allows you to then take the total area of steel and allocate it to long and short bars based on these inputs. So if you want to do this by user definition, you would select user defined. All of these inputs then become editable by the user. If you select none, the program reverts back to this. If we select adapt, the program actually takes this format and plugs it into the curtailment schedule. And then if we use ACI 318, we have some predefined parameters there as well as for Eurocode. And there are additional options and rules with how the program handles the reinforcement placement per these options down here. Okay, we're going to select none for this example. We're just going to go back really to the legacy way that the program handled the rebar, which is this input here. Finally, we can determine the different load combinations at strength level and also service level. So in this case, we're designing these as gravity-only members for these beams. We have a couple of strength combinations, including dead load, live load, self-weight, and also the hyperstatic or the secondary actions from the post-tensioning, and also service combinations that we'll use to evaluate the stress and deflections. We also have a specialized combination here called initial, where we're considering the self-weight and 1.15 times the post-tensioning for evaluation of the initial condition when the force is transferred into the member. And this will help us check that allowable 3 times square root of F prime CI in tension. If that's exceeded, the program will add rebar to control the cracking initiated by that overstressed condition for initial. So we'll go ahead and select OK. I'm going to save the file. Okay, once the file is saved, I recommend running the files locally on your machine. If you're running them off of a network, make sure you map the drive onto your local machine where the file resides on the server that you're running from. But once we're done entering the data, we're going to go ahead and we can use this icon to save, execute, or just simply select execute. And the first part of the process really is for the program to generate a solution for the post-tensioning. And this will result in ending up here in this PT recycling window. We call this informally the recycler. And so we went through a lot of the details for this in the one-way slab example. One-way slabs and beams are considered quite similarly in the program. So much of what you see here is applicable also to that one-way slab example. In this case, there's just a heads-up dashboard here that shows us a few of our different checks based on the parameters that we input. So for PT force, min and max, which was 150 to 400, P over A, this is just the pre-compression in PSI, you can see that the program has determined we need a force of 397.3 kips in the beams. If we were to break this out on a per unit width per foot, we would need 37.8 kips per foot. This is over the flange. 44.1, 37.8. This doesn't really apply for a beam because we're depositing all of that force into bands within the beam stem typically. We have 15 total strands in the beam. The P over A is 150. This gives us a hint that it's likely that the controlling factor in terms of the design parameters was actually minimum precompression. And to determine that, we can go over here to required PT force. This is tab number 3. And we can see the required force to meet minimum P over A was right around 397. The required force to meet the allowable stresses was only 295. And then balance loading was around 210 to 11. So P over A controls this design. The percent of dead load that we're balancing is right at close to 100%, just below. So that means that the balance loading min and max, that was 50 to 100. This is okay. The stresses for tension and compression are okay for service. So if I go over here to tab 4, we can see for sustained, we actually have slight tension in the outer bays. This is a coefficient times square root of F prime C. This is 0.07, 0.8. The allowable was 7.5 square root of F prime C. So this beam is almost fully precompressed at the sustained level. At total load, we have a value of around 3 square root of F prime C. So this again is satisfactory. At initial condition, because the beam may be oversized for the loads on it and the spans, it's pretty common where you meet these sustain and total conditions fairly easily, that initial could potentially exceed allowable because we're actually providing too much post-tensioning in the beam, which causes some stress at the opposite side of tension face in the service total condition. But you can see here these exceed 3. So the program, even though this says no good, that's just an indication that the stress is no good at that initial condition. The program will add reinforcement to meet that requirement per the design code selected. So here we're using tendon A only. If we go to graphs, this will show this red tendon is tendon A. This is the profile. This is some of the stress graphs, and you can change between top and bottom fiber, total, sustained, etc., initial, and we can check stresses. You can see for sustained top fiber, it's completely in compression, and bottom fiber, there's slight tension here and here. The gray shows the permissible envelope of tensile stress in the member. If we flip this back over to total, that stress grows because we have more live load on the spans, those end bays, and there's a little bit of tension in the midspan. So this gives some good information in these graphs. What I wanted to mention about the actual tendon shape, tendon B and C are not currently active. If they were, we would see those in blue here. And if we wanted to introduce those into the design, what I can do here is I can say, okay, I want to use tendon B. Well, tendon B is defined in tab number 5. Tendon B, if I press Control and hold that down, I can move the tail for tendon B. Or you could enter it directly in this table. This is a fraction of the span length. So tendon B is basically an add tendon in the left span. Tendon C is in the right span. If I enter a force for those tendons, I'll say I want 50 kips in tendon B and in tendon C, and maybe I want 50 kips here. You'll notice that the total force A plus B plus C changes in this block. So this is based on all tendons summed up, 447, 397, 447. This just shows you the current tendon that is selected over here. All right, so now once you make a modification, we can recycle and the program will update the results. So now you can see in the graphs, we show those blue tendons. We show a graph also of the force, the effective force. So we have a decrease in the center span, that's 397. The two outer spans are 447. And this allows you to interactively make modifications to the system, including making modifications to the control points if needed. Left top, center, right top, this is span 1, and that just repeats for each of the spans. So we really don't need those two add tendons. I'll go back and I'll reset those to 0. Those are not required in this case. I'll recycle again. If you ever exit the recycler, come back into the recycler and you want to bring up the previously saved solution, you can select recall and then recycle. You don't have to enter the data again in this dialog. Once you feel satisfied with what the program has produced here, or satisfied with the modifications you've made, and then having recycled it, we're going to exit. Once we exit, the program will calculate reinforcement for serviceability and strength, and also it would calculate the deflections. This comes back into what we call the shell of the program, and now we can look at the report in a tabular format using what we call a report generator. We can just look at raw graphs for the solution. This is really on a load case basis, an envelope of load combos, and then we can also look at a summary. This is both graphical and tabular. So we're going to use the summary first. If we go to the summary, this allows us to check different combinations. Min and max would indicate that skipping is active. So we have, a maximum and minimum range of results for the live load that was placed in the different skip patterns. And then we could also check the envelope. If I go to envelope and look at, for example, the summary report, this is the most commonly used report for information relative to the design. So this summary report would show us the geometry in elevation, the top reinforcement. So this is the reinforcement in the beam needed at the top. Bottom reinforcement. If I change this to a different combination, this will reflect what's required for that combination. So for example, if I go to initial, we saw we had initial overstress. We actually need some bottom reinforcement at supports due to initial. So for example, at an interior support, because we have so much post-tensioning and very little counteractive dead load, we actually develop tension on the bottom fiber at that initial condition, so that we need this rebar to control that cracking that may occur under that temporary condition. And that's added to the design. It's included as part of the envelope here that we generated first. So this is our envelope. In the envelope, we can also see we have the CGs for tendon A, B, and C. B and C are blank. We didn't use those in this design. And also the force in each span for this beam. We have some graphical results for the amount of steel. This is just area of steel at different locations along the span. Required versus provided. Provided is this blue line. Required are the different tick marks, the different sections for the beam. Shear reinforcement, this just gives a summary. So this kind of indicates where you need the shear reinforcement and the spacing. For more detailed shear reinforcement output, I would recommend using the report generator. I'll show where that is as that example. And then we have additional design parameters, quantities. If you go to the second page, we also can pull up the deflections for each span. This considers long-term deflection or creep multipliers assigned to the sustained loads, plus additional deflection due to incremental live load under sustained and total. So the maximum deflection here for this beam system with consideration of long-term multiplier is about 0.14 inches. So this is reflective of the report you would also be able to produce in the tabular report under block number 14. That's builder sum. Also for builder sum, if you, for example, pull up a service combination, you could check stresses. That's something that is sometimes valuable to evaluate. You could also check moment diagrams, shear diagrams for any of the combinations selected here. If you close builder sum, which is just a submodule of the program, you can also produce graphical results based on just the raw outcome of the design. We have bending moments for different load cases and the envelope of combinations, shear, deflections, and also the PT required versus provided, and again the geometry of the system. And finally, if you wanted to produce a tabular report, we could go to the report generator. This allows us to customize a report or use a predefined report based on level of accuracy or level of detail rather. So we could choose, for example, a concise report, which just preloads the report with these different settings. If I choose concise, or I could say I just want certain blocks of that concise report. The most common report used is probably this compact report, which breaks the results really into left, center, right per span, more zonal type results versus detailed results at each section. Detailed results would be they would pertain to this option for tabular reports detailed. So this would give you results at every 20th point along a span for the design. If we go to shear reinforcement, for example, and I'll even do the detailed shear here, and then I might call this, I want to save this maybe as a default or save the selection. So maybe I want this to be a customized report. I'm going to call shear beam. We'll select OK. And that would then load into this pull-down menu where you could recall it as needed when you create a report. I'll just go ahead and create that report just by selecting or having selected the shear for detailed and compact. This is going to allow us then to save the name of the report. The report will open as an RTF document in Word or whatever your word processing program is set to as the default on your system. This is our report for shear along spans 1, 2, and 3. You can see this gives us requirements, spacing of shear at each 20th point, and then the detailed shears breaks this out into each individual load case. So this gives the shear along 20th points for each individual load case in this example. The compact shear gives you the required area of steel and spacing based on the envelope of strength combinations. So this is not broken out into individual load cases. This is just the envelope at ultimate level for the shear. And again, any report that's available in the report generator can be produced in this tabular format in this way. If you have any questions about this tutorial, please contact us at support@adaptsoft.com, and please check the PTRC playlist that will include other videos that may be of interest for use of ADAPT PTRC.